Okay, now. On the previous tutorial, you noticed that we just expanded our knowledge about the R-stand arm by using the function which is what's called the prior summary in order to extract the priors which they have been incorporated into our model because we needed them in order to just make an inference which is going to be our posterior density in the parameter space about our parameters of interest. However, at this tutorial, I'm just going to talk about these three blocks that we have here. We have the intercepts, prior for intercepts. We have the prior for the coefficients. And also, it's kind of the second block. And also the other thing that we notice here, there is a block, which is going to be our third block, which is called the prior for the auxiliary, which is going to be the sigma. I'm just going to talk about these ones, how they have been decided, how they have been adjusted, and how we can change them ourselves manually. And also, at the end of this tutorial, you're going to see how we can visualize the impacts of a prior on, let's say, the true values that we have on our analysis there. In order to do that, I'm just going to go to, I should say, to these notes that we have prepared so far. And on the very last page that is blank, I'm just going to talk about those ones. Okay, so far, the things that we have seen, it was very straightforward. We said that, okay, we are just going to come here and say that in our women data sets, we are going to talk about the height of those women. We said that the heights is going to be a kind of a normal distribution, that this normal distribution, it bears a parameter for itself. And that's what we said. It said that it bears a parameter by itself, which is going to be its mean, which is nu. And also, we said that it has also a sigma, which is going to be our, I should say, a measure for the dispersion, or something that we call that the sigma as something which shows our uncertainty about the true mean of our distribution. However, we said that we design a kind of a parametric model. Why we say that it's going to be a parametric? Because we notice that we say that, okay, the mean that we have here, it's going to be given by a linear function. We said that the nu, which it was the mean of the woman's height, is going to be given by this function. Let's call that ax plus b. This is the easiest model that we decided to just incorporate into our model. We said that, okay, this one is going to be the a. We said that a is going to be our slope and b is going to be our intercept. And that was the reason that we just ran our Bayesian model to make an inference about the true value and the confidence level and the credible interval that we had for the levels of the slope and the intercepts that we had. Now, however, what do we mean by defining a prior for this? Imagine that if x relates, let's say, to the weight. And what do we mean by the priors that we are going to talk about these ones? We are just going to go back to a more general format of our analysis. Imagine that we have, let's say, y, which it can be even nu. It's going to be given by an intercept b. And also, the other thing which is going to be relevant about the model that we have right now, it's going to be added by, let's say, for example, let's call that beta 1. Let's use it I. We have, for example, a1 as x1 plus a2 as x2 plus it goes higher terms as ak xk. Each of the x1 and xk, they are going to be our covariates, and however, at the same time, we know that the coefficients a1 and ak, they are real numbers which define the slope of our parameters, the slope of our model. In this case, we come here and design, I should say, the priors for our model, essentially like that. We say that, imagine that the AK it's going to be given by a normal distribution, which in our stand arm, the measure of the center is going to be centered at 0. However, for our sigma, we said that the sigma we are going to have in our stand arm is going to be (2.5) multiplies by a ratio that we call that this ratio is going to be the standard deviation of our covariates, which is going to be the x, divided by standard deviations of our covariates, which is going to be the y. Then that's what you saw it over here. Let's go back to the codes that we have done. Look at the second block. The second block that we have for the coefficients, it's about all the coefficients that we have in our model. We have specified priors. Our specified priors, you see that. Specified priors is essentially the priors which defines all the coefficients in our models. It says that the location, which is going to be the mean of the value, is going to be essentially 0. That's always our stand arm specifies. It centers the distribution. That's why you will see that the location is going to be 0, because even by a very single transformation, you can always localize your distribution at the center, and that's why you have the location to be 0. However, for the scale, it is always predefined with the R stand arm that it has to be 2.5. We have, I should say, 2.5 units away from both directions from the mean, which essentially covers most of the distribution. However, you see that the adjusted prior, again, is the normal with the same, I should say, mean, with the same the location, which is going to be, I should say, 0, which is centered at 0. However, the scale is 0.72. How the scale has been changed, this is the thing that we can just talk about that right now. We said that the center has been changed because we have our initial, I should say, 2.5 value there, which is, as you can see, this is multiplied to a ratio, which the ratio is the standard deviations of your covariates x divided by standard the standard deviations of your, I should say, your response variables, then, which is very easy to find it. You can just go to the R. You can simply write the code for the ST of your heights divided by the ST of your weights and multiply that, let's say, by 2.5. Then you get what? You get 7.2. It's very easy to calculate the standard deviations in the R. I'm just going to do that. ST. You can see that. You can just put the ST. And you can just write it as the data sets as the woman. And you know that in the woman data sets, your X value was supposed to be your weight, the woman's weight. Simply can find it. I can store that into an object as I call that SDX, which is going to be our standard I should say deviations of our covariates. I stored that into STX, and at the same time you can find the standard deviations of your response variable. Your response variable comes from the woman's height, which is going to be the woman's height. I'm just going to run it. You see this result. I'm just going to store that into an object which is called STY. I'm going to store my object there, and it's going to be STY. And you see that it's going to be a very easy calculation that you can just, as you notice, that it's going to be the ST of X. It's going to be a very simple calculations that we had before. Then you see that the thing that we're just going to do, it becomes simply as this one. We can come here and say that, okay, the ST Y divided by, I should say, let's say divided by SDX. That's what we have here, and that's the ratio that we have. And now the thing which I'm just going to do, I'm just going to multiply that into the standard measures that we had, which is going to be multiplied that 2.5. And you see that, okay, that's the value which we got from this one here, which is going to be the scale, is going to be, now it is a scale to 0.7.2. And that's the thing that we had, oh, sorry, just I had to erase this one, and I said that it has to be SDY by SDX. SDY by SDX, and you see that as what we did over here, that's now we have the scaled measure is reduced by 0.72, and that's the thing that we see that our prior is now being adjusted. Okay, now, however, also we are going to talk about the auxiliary, and I'm just going to go back to see what do we mean by the prior of the auxiliary. Look at the other parameters in our model that we have. The other parameters in the model that we have, it's the parameters which is, I should say, as you can see, this is defined by the sigma. That's what is called as the auxiliary. This is the auxiliary parameters. And as always, you see that, if I just go back to, if I want to show that in the models that we have, we always, this is assumption that the sigma it is defined as an exponential distribution with the parameter equal to 1. However, when we just go back to the thing that we see over here, we see that our adjusted prior for exponential is, although initially is specified as the exponentials with the rate 1, it is defined as exponential as with the rate 0.22, and you can see that the adjusted one, it's going to be multiplied to or divided by the standard deviation of the y. Standard deviation of the y. We can see that also, you can see that you can measure the thing which has happened here. You can decide it to SD, 1 divided by SDY. It's going to be 22. That's right. And you see that the adjusted prior, now it has exponential with the rate, which is rate equals to 0.22. However, we just go back to one other important and crucial information that we had in our model, which is essentially the priors for the intercepts. The prior for the intercepts, it's, you see that that's the model that it comes with extra piece of information that's after predictors centered. And what does it mean? It means that sometimes, look at that. When we talked about, I should say, the model of the intercepts, you know that this is something very easy in the math. When we design a model like that, y equals to ax plus b. When we design a model like y equals to ax plus b, sometimes the thing that we have is that the interpretation of the b is going to be very interesting. Because we say that, what is going to be the value of, I should say, of the y when we have the 0, I should say, for the covariance x. Imagine that if our model y is going to represent the height, which says that equals to a times weight plus b, the understanding that we're going to have about b is that what happens when the weight is going to be 0. We say that what is the height? When weight is equal to 0, which is somehow kind of a preposterous thing. We cannot come with this answer, how much is going to be the height when the weight is going to be 0. And in most of, I should say, the physical and the real life examples of the intercepts it comes with that, I should say, with that kind of singular interpretation when we look at the 0 point of our covariate step. Then when you just come to our model here and you say that the after predictor is centered on the intercepts for the priors, you will see that it's essentially nothing except the fact that this one has been centered to just resolve that issue. However, when we just want to talk about, I should say, in our R stand arm, the normal priors come with this one. The intercepts B. I write that the B intercept. In R stand arm, it's always a normal distribution, which essentially our mean here is going to be, I should say, the mean of our response value. However, for this one, we have also again 2.5 multiplies to a ratio that, as you are going to see, is going to be the standard deviation of our response value y. Okay, and now let's go back to our R to see what has happened there. For our intercepts, apparently for our normal specified priors, we said that we have localized that into, let's say, into the R, which is the mean is going to be 65. It's going to be very easy to verify that. We say that the mean of women of their height, which is going to be our response value, you see that we get the result of 65. And that's the thing that we have just taken it here. Our intercepts, the specified priors for that, it's a normal distribution, which is localized at the mean, which is the mean of our response value, and the scale, which is the dispersion away from that, it's always fixed as 2.5. However, when we just come here to the adjusted prior, we see that this one, the scale is 11. And as we said that we have to multiply that, it's going to be very easy. When you multiply that by standard deviation of the y, it had to be standard deviation of the x. Now it's just, let me go back again. Oh, sorry, I just made a mistake, and I shouldn't just multiply mean by that number. I had to just multiply, as you notice, 2.5 times the standard deviation of y to get the adjusted value for that, and you see that the scale is 11. Sorry, I just made a mistake, and I multiplied the mean by the standard deviation of the y, which I got a completely wrong number. And as you notice from the thing which I have written here, in order to make the adjustment on the value which I had to multiply 2.5 into the standard deviations of your responses, which in our case, our response value, I should say, feature is going to be the woman's height that we have in our Americans women data sets. And now you see that when you just multiply the standard 2.5 deviation times the standard deviations for our response value, we get the exact value for the 11, which is going to be the adjusted value which we had before. Okay. So far, we have done a great thing so far. We have been able to see the impacts of how to just make these adjustments on our results, on our Bayesian regression analysis. And I think that's going to be a